Ever wonder how substances stick to surfaces, or why your tea infuses the water in your cup? Welcome to the fascinating world of adsorption kinetic models. This captivating field of study explores the process of adsorption, where molecules from a gas or liquid adhere to a surface, creating a film of sorts. This process is not just science jargon, but it's a fundamental phenomenon that impacts our everyday life. From the way detergents clean, to how pollutants are filtered from water, and yes, even the steeping of your favorite tea, adsorption plays a crucial role. Within this intriguing world, two distinct types of models stand out: the linear and the nonlinear adsorption kinetic models. Each provides a unique perspective on how adsorption occurs and offers insights that are pivotal in various scientific studies. Now that we've set the stage, let's dive deeper into each of these intriguing models. First off, we have the linear adsorption kinetic model, a simple but powerful tool in understanding how substances interact. This model, with its straightforward approach, is a perfect starting point for those delving into the world of adsorption kinetics. Its simplicity lies in its assumption: the rate of adsorption is directly proportional to the concentration of the adsorbate. This model is not just simple, it is also versatile. It has been used in a wide range of scientific fields, including environmental science, chemical engineering, and even in the field of medicine. For instance, in environmental science, it is used to study gas adsorption, giving insight into how pollutants interact with various surfaces. In water treatment processes, it helps to understand how contaminants adhere to activated carbon or other filtering materials. Despite its simplicity, the linear model offers an effective way of understanding adsorption kinetics. But what if we need a more comprehensive model? Enter the nonlinear adsorption kinetic model, a more complex but detailed approach to understanding adsorption kinetics. This model, unlike its linear counterpart, doesn't assume that adsorption rates are directly proportional to the concentration of the adsorbate. It instead takes into account the fact that at high concentrations, adsorption sites may become saturated, slowing down the rate of adsorption. This gives the nonlinear model a certain richness. It can provide more in-depth information about how adsorption takes place. This makes it invaluable in advanced studies, where understanding the fine details of adsorption is crucial. The nonlinear model is particularly useful for modeling adsorption in complex systems. Think biological systems, where the adsorption of a drug onto a cell surface can be affected by a multitude of factors, or environmental processes, where the adsorption of pollutants onto soil particles can be influenced by pH, temperature, and other variables. The nonlinear model, with its complexity, provides a detailed understanding of adsorption kinetics. But how does it compare with the linear model? Now that we've explored both models, it's time to lay them side by side and see how they measure up against each other. The linear adsorption kinetic model, with its simplicity and straightforwardness, is a go-to for many. It provides valuable information about adsorption rates and equilibrium concentrations. This model is particularly useful in situations where the adsorbate concentration is low and adsorption is relatively quick. On the other hand, the nonlinear model dives deeper into the process of adsorption. It accounts for the complexities and variables that the linear model overlooks. This model shines in situations where the concentration of the adsorbate is high and adsorption is a slow, intricate process. It provides a detailed analysis, revealing more about the adsorption dynamics. So, the choice between the two comes down to the specifics of the situation and the level of detail required. So, whether it's the simplicity of the linear model or the detailed analysis of the nonlinear model, both have their unique strengths in helping us understand the fascinating process of adsorption.